So let's get started. So in the last class, so let me do a quick recap of what we did in the last class. So I think we started looking at a few example problems. For example, the PCA was one example, and then we looked at various optimization problems that hopefully eventually we'll look at how to solve this. But these are the ways by which you can pose the optimization problems, right? Depending on the applications. So towards the end, we saw what is known as linear separation problem. Essentially, you have two data sets. And you have to separate it by a hyperplane. So all that you have to do is, basically, let's say you have one set of points like this and the other set of points like this. Then you have to separate it by a hyperplane that is quote unquote robust, right? What do you mean by robust? Because I can separate this by placing a hyperplane very close to, let's say, one of these points, right? In that case, when you deploy it in the field, because of noise, some points may lie to the right, in which case you will make a mistake, right? So you should optimally place, in the sense you should place it at the center, right? The question is, how do you pose that as an optimization problem? Essentially, what you have to do is find out the distance between the plane and the nearest point in one set, the plane and the nearest point in the other set. You try to maximize that distance, right? So essentially, what do you think is the solution? Can somebody guess? You have to place right in the middle, right? So that's the solution. So the question is, what should be the optimization problem for which you get this as a solution, right? We will see that maybe a little later. Okay, so today what we are going to do is we will start with optimization problem from today onwards. Okay, so how do you solve optimization problems? Okay, so let's start with some basic calculus, and then we will move on to I'll give you some sample optimization problem or a general form of optimization problems. And then we'll start with a very simple optimization problem called unconstrained optimization problem, and see how to solve those. Once we do that, then we will move on to constrained optimization problem, which is very relevant for most of the data analysis kind of applications. We will see how to solve such problems, right? So let's start with the some prelims. So let's look at a function. So typically, the kind of functions that we deal with will be a map from Rn to R. Right? Can you give me an example of a map from Rn to R? Huh? Norm, yes, good. Norm, inner products, right? Well, you fix one vector and take the other vector as x, right? X transpose v. So that's another example of a function, right? So you take a function. So now we know the notion of continuity of a function mapping from R to R. So what do you mean by continuity of such a function, right? So we say that f is continuous at x belonging to Rn. See, this x is a vector, okay, n-dimensional vector. We say that it's continuous at x if you take any sequence that converges to x, right? If for every xn converging to x. So what do you mean by xn converging to x? What do you mean by that? If you have a sequence of numbers, I say that xn converges to x, you know what it means, right? It will enter the epsilon room no matter what epsilon is after some time, right? That's what it means. Now, what do you mean by a sequence of vector xn converging to x? What do you mean by that? You should take an epsilon room around x. So what do you mean by an epsilon room around x? For scalars, epsilon room is essentially an interval around x, right? Of size epsilon by 2 on each side. So the total length is epsilon. So now what should I do here? You look at an epsilon ball around it, right? So you take a ball of size epsilon, that's my epsilon room. And you look at the sequence xn, which is a vector. Eventually that vector enters that room epsilon, right? Epsilon rule.